My name is Christy Anthony. I'm a board member of CHASS and I have the privilege of cruising us through the afternoon as your new MC for the day. Just so you know who I am, I work for Festivals Adelaide, which is an alliance of 10 of the most unique festivals in Australia that happen to be in Adelaide, and also for the magnificent Flinders University. It's my privilege and honour today to be introducing Professor David Christian. David is by training a historian of Russia and the Soviet Union, but since the 1980s has been interested in history at very large scales. He's director of the Macquarie University Big History Institute, which founded in 2012. Over the next few years, he will also be working with the support of Bill Gates to create an online course in big history for high school students. In 2010, he became the inaugural president of the newly created International Big History Association. Today, David will be talking about a planet-changing species, the role of humanities in the Anthropocene. In the last 200 years, our species has become a planet-changing species. This is remarkable because it's the first time in the 4 billion year history of life on Earth that a single species has played such a role. What is it about us? The humanities surely have a crucial role to play in explaining and interpreting the remarkable role of human beings in this era. Please make him welcome. Where are you, David? Professor David.
Okay, thank you very much for that kind introduction. I've very much enjoyed what I've heard so far. I found it fascinating, and I do hope that what I say is of interest. This is a very diverse audience, and I'll cover a lot of territory. And I'm going to try to talk for no more than 30 minutes and leave time for questions. So let me begin with this picture. I first used it as a sort of icon for thinking about the Anthropocene in a conference run by Ian McCalman in Sydney a year ago. I realised later that it's actually a composite. I really liked it. I thought it's a great icon for the Anthropocene. Taken by a Ukrainian historian, Yevgeny Khaldei, and those are British hurricanes up in the air there. Let me begin with, I know it doesn't really make sense, one shouldn't take institutional logos seriously, but let me just look at, I was just looking at the CHASS logos. First, the slogan, what makes us human? It's tempting to just gloss over slogans like this, but it's a fantastic question, and in my book, it's absolutely at the centre of what humanities are. It's a question we're often taught to think is impossible, unanswerable, beautiful, interesting, important, but I actually think we can answer it. I think there are some reasonably powerful and simple answers, and I'm going to suggest one in this talk. And secondly, we've got an emblem, and it's a spiral. Now, if you start small and if you start big with the big dots and you go inwards, you're going sunwise or clockwise. If you start small and you go outwards, you're going. My wife tells me the technical term for this is widdershins, which is anti-clockwise. Now, what I like about this is the fact that it goes both ways. It goes from the very small to the very large in one direction, but it also goes from the very large to the very small. And in a sense, that's what I'm going to do. And I'm going to argue that we can understand humanity, the humanities, the human in new ways if we do this, and that's what big history does. So here's the structure of this talk, so you know where we're going. I'm going to begin by talking about what big history is, on the assumption that at least some people here are not sure what it is. And I'll try and give a quick feeling for what we do in big history courses. Secondly, I want to talk about how the story of the universe, which is what we tell in big history, can illuminate the humanities. And I'm going to focus on a particular theme or a particular pair of themes, energy and complexity, and the relationship between them, and how they can, I think, suggest new ways of thinking about human history. And I'll be asking the question, how did energy flows shape human history? And then I want to talk about the humanities and today's world, the Anthropocene. And I will argue, as I suggested in my abstract, that we live at an astonishing moment. Now, this is not just rhetoric. This is an astonishing moment on a scale of 4.5 billion years. Nothing like what's happened in the last 200 years has happened in 4.5 billion years. Now, that makes us interesting. By some arguments, in astrobiology, which is becoming a serious science, some people would argue this is an astonishing moment on much larger scales. If it's true that we are pretty close to being unique in the universe. And finally, I'll end with a plea for linking the humanities and the sciences much more closely on two grounds. First, that the humanities have a huge amount to gain by seeing the problems they discuss in the larger context of the sciences. And secondly, that the sciences too have a lot to gain from the insights of scholars in the humanities who deal all the time with levels of complexity. Now, I hope scientists in this room will not resist this too hard, but levels of complexity that are much higher than those dealt with in the natural sciences. Okay. So what is big history? You can think of it as a bridge between human and cosmological history. Trying to sort of put together stories from different disciplines. So we get a story of a sort of history of the universe, and then we ask the question, what is the place of human history in that? This is a definition of big history from the International Big History Association website, and I think it's a pretty good one. Big history is the attempt to understand in a unified, interdisciplinary way the history of cosmos, Earth, life, and humanity. To illustrate that, let me explain why I love using Van Gogh's Starry Night over the Rhone as a sort of icon for big history. We have stars and the cosmos. We have astronomy, in other words. We have planet Earth, so we've got geology. We've got our home planet. We've got water, which is where life evolved. So we've got chemistry, we've got biology. We've got cities, churches, and civilization. We've got anthropology and history. We've got electric lights, we've got modernity, so we've got science and technology. So big history inevitably, given its project, connects disciplines all the way from cosmology to modern history, even futurology and studies of today's world. And finally, and perhaps most important of all for the humanities, we have you and me trying to figure out how the hell we fit into this large story. The people who are telling the story, who are perceiving the story. So what's the story? I've referred to the story. Well, as I teach big history, over many years, slowly a story has come into focus. Now, I don't think it's the only story you would tell, but it's the one that I find most engaging, and it's one in which humans play a huge role. So it goes like this. The early universe was very, very simple in all sorts of ways. It had very little structure. Think of a kind of thin mist of hydrogen and helium atoms embedded in a sort of pudding of dark matter, which we don't really understand. There are photons of light traveling through it, and the whole thing is incredibly homogeneous. And one way of saying that is to say that the whole thing is, in terms of temperature, very homogeneous. This iconic image here from the Planck satellite is measuring tiny temperature differences in the cosmic background radiation. And the difference between the blue and the red areas is about 1/1000th of a degree. So this is a very simple, homogeneous early universe. I'm talking about the universe, say, 500,000 years after the Big Bang, probably up to about 100 million years after the Big Bang. So there are no galaxies and stars, there are no heavier chemical elements, no planets, certainly no living organisms, no human beings. This is a very simple universe. Then, and this is what the story is about, over 13.8 billion years, more complex things emerge. And emerge is the precise word to use, because the idea of emergence works very well in big history. Now, let's be clear, we're not saying the universe got more complicated. Most of the universe today is still extraordinarily simple. But in little pockets where the Goldilocks conditions were just right, such as around a rocky planet orbiting a star, you get conditions that allow the creation of more complex things. And you also need gradients of energy to do that, as we'll see, and I'll come back to that. So in these environments, more complex things have emerged, and complexity has built on complexity. And when they emerge, they have new qualities, and that's emergence at work. So something utterly new seems to appear, for example, with the appearance of life. Now, this is not a story that's irrelevant for human beings. And one of the reasons for saying that is there are very good reasons for thinking that modern human society represents one of the most complex entities we know of within the story. There may, of course, be more complex entities, but modern human society represents a very, very high level of complexity. Now, the way I tell the story, and again I emphasize it's not the only way, is to use a skeleton of what I call thresholds, 8 thresholds of increasing complexity. They build on each other. Each threshold is a moment in which something new appeared, and the very first is the universe itself. And you'll see how these thresholds take us across many paradigms of modern scientific thinking. Science in the very broad sense that Ian Chubb alluded to this morning, the definition of science used in every language apart from the English language as rigorous empirical scholarship. Threshold 2, the first stars, astronomy. Threshold 3, the creation of chemical elements, new chemical elements in dying stars and supernovae. Threshold 4, using those chemical elements in a chemically enriched universe to create new objects, such as planets, which are chemically much more complex than stars. On those chemically enriched environments, life becomes possible. We know it was possible once, but I think the odds are increasing that life is quite common, at least bacterial life in the universe. Now, this is controversial. I argue that the appearance of our own species counts as a threshold in this story. And actually, the controversial nature of that claim makes it a very interesting pedagogical tool. With students, we can debate. And I'm going to try and demonstrate, I'm going to try and explain why I think that's true. And then 2 more thresholds within human history, each, as I will argue, associated with a sudden increase in energy flows that allowed increasing complexity. And our courses end by looking at the future. If you look at the past on these scales, you're talking about processes that have huge momentum. And it's actually our students that really pushed us to asking questions about the future. So this is a fabulous way of helping students link what they know about the past to their thinking about the future, including the near future of climate change, declining biodiversity, and so on. Now, this graph, let me introduce these themes of energy and complexity. This graph comes from an article by Eric Chaisson, an astronomer who's taught an astronomer's version of Big History for longer than I've taught my versions. He's taught these in Boston. And he calls this cosmic evolution, not big history. The vertical axis shows, I won't try and point because there are 2 screens, but it shows energy rate densities. Now, it's a very simple idea. The amount of energy that flows through a gram in a second. So this is sort of the density of energy flows. And what he does is he calculates, these are back-of-the-envelope calculations. He calculates the energy flows through different things. And here's the answer he comes up with. Through the sun, about 1 erg per gram per second. Now, he's not being over-precise. If you look in the bottom right corner of this graph, you'll see a mini graph which shows a range of possible answers. And they range over at least 3 orders of magnitude. But nevertheless, that's 1 erg per gram per second. Do the same calculation for modern human society, and you're talking about energy flows that are 1,000,000 times as large. Now, he doesn't claim great precision for his calculations. It's the orders of magnitude that are striking. And the point of this is that it suggests something that really ought to be true anyway, that more complex things require larger energy flows. In a universe dominated by the second law of thermodynamics, things tend to break down. Building complex things requires flows of energy. So we expect that more complex things, by and large, all else being equal, will require larger flows of energy. The horizontal axis shows how long these things live, and it hints at another idea, which is that more complex things may live shorter lives than simpler things. To put it bluntly, you will not live as long as the sun. The sun is much simpler than us. So, here are some sort of very simple theoretical ideas. Sorry, I couldn't resist this. I gave a talk in Tianjin in China 3 weeks ago, and they took some fantastic photographs. And this is from it. And I gave a talk with a Chinese colleague who gave a Chinese take on big history. And he was talking about Confucius, and he was talking about the union of heaven and earth. And it was a wonderful session with him. So here's the short course. So here's a quick course in big history. And it consists just of a number of dates, so you can get a feeling for what we cover in a big history course. We cannot deal with dates like 1 million or 1 billion. Our minds are just not designed by natural selection to do that. So I found, divide all the dates by 1 billion, and it's much easier to get a sense of proportion. So that's what we'll do. Let's imagine the universe was created 14 years ago, and here's a series of dates, and I'll run through them quickly. The universe would have existed for about 14 years, the Earth for about 4.5 years. So the Earth has existed for about a third of the history of the universe. That itself is an interesting piece of information, I think. Living organisms would have existed for about 3.5 years. That is very interesting because it suggests that life appeared on this planet almost as soon as it was possible. And that suggests that the universe as a whole may be bio-friendly, at least to bacterial life. Because the next threshold here is large organisms with many cells, and they appear on this timescale only 7 months ago. That suggests creating large organisms is difficult. That may be why the SETI project has not yet encountered alien civilizations. Many of you will know that an asteroid wiped out the dinosaurs 67 million years ago. That's 3 weeks ago on our timescale. And by the way, in case you think this must be a deterministic story, it is seriously not. If that asteroid had been on a trajectory 5 minutes earlier, 5 minutes later, the dinosaurs would still rule, and you and I would not be meeting here in Melbourne. It's as simple as that. So contingency operates at very large scales as well as very small. Our own species would have appeared 53 minutes ago. Agricultural societies 5 minutes ago. As a historian, I love this because this is when most historians get interested in the story. And I can't resist the temptation to say, you may be missing something here. Like 13.8 billion years. The entire recorded history of civilization would have lasted 3 minutes, modern industrial civilization for 6 seconds. Now, the payoff for the humanities, well, this is a ladder of complexity, if we've got this right. And complexity builds on complexity. So human history, the humanities in general, are dealing with an extraordinarily high level of complexity. No wonder the humanities don't yield clear, mathematically precise paradigms in the way that the natural sciences do. Getting a Kuhnian paradigm is going to be much tougher here. We're dealing with very high levels of complexity. Now, let me try and talk about human history as part of cosmological history. And I'm trying to keep track of time here. No, it's not letting me in. Okay, human history is part of cosmological history. What do the humanities gain by placing human history in such a large context? So let me try and suggest some answers to that. Well, awareness of the complexity of the humanities, I think, is an important insight. Profound complexity. But also continuities between the human and the cosmological story. And it's those continuities I want to talk about by focusing on the link between energy and complexity that I've already touched on. Now, if it's true that complexity requires energy flows, then every time we see something complex, we ought to be able to ask, what's the energy flow that allows that form of complexity? So with stars, we know what it is. It's fusion. It's what happens in an H-bomb. So fusion explains how stars work. So astronomers are interested inevitably in fusion. This is what drives the structure of stars. In living organisms, we call it metabolism. Metabolism is a central concept for biologists precisely because if you describe an organism's metabolism, you're describing how it taps the energy that allows it to maintain its structure. So here's an egret. It's about to capture a long tom for breakfast, and that's its way of getting energy. So to understand living organisms, you must understand how they tap photosynthetic energy. And if you understand that, you understand a lot about the organism and a lot about its relationship to its environment. So how they tap energy is crucial. Now I'm thinking, so how do energy flows shape human history? I'm embarrassed by how long it's taken me to see the links between big history and my own work as a historian. I'm so much part of this highly specialized world of education and research. It's taken me years to see these links, but I'm beginning to see them, and this is how they go, I think. Here's a big history question. If increasing complexity is fueled by flows of free energy, shouldn't historians be studying those flows of energy? And shouldn't they have a lot to tell us about the trajectory of human history? So let me explore this question a bit. If you ask that question very quickly, I think you find yourself concluding that the human relationship to energy is very unusual indeed. These are the normal rules in the biological realm of energy extraction. A species evolves within a particular niche, with a particular, let's say, metabolic gadget, a particular way of extracting the energy it needs to survive. It's got a particular metabolism. Its populations expand until it's exploiting all the energy that is available within the biosphere, given the nature of that gadget. And then they fluctuate around that norm. And then eventually the species goes extinct or it evolves into something else. That's the normal pattern. So it yields a graph like this. The figures, by the way, don't mean anything. This is just illustrative. There's a limit to the energy available, and populations fluctuate around that. Now, here's a graph of human population growth over 100,000 years. And I hope it stands out immediately that this is something very different indeed. Here's population growth in the Paleolithic. Now, we can actually track this growth with increasing precision. By 10,000 years ago, humans occupy all continents on Earth apart from Antarctica. Then we get the agrarian era, agriculture from 10,000 years ago, and populations rocket upwards, and then we get the modern era. And a lot of that astonishing spike occurred during my lifetime. So this is a very strange pattern indeed, and very different from that of other animals. So what's going on? What makes us different? And I hope it's obvious that this is very close to the CHASS question. What makes humans different? So here's a hypothesis I've worked with for a long time, and I think it's a pretty good one. It's pretty close to the truth. It may not be absolutely precise, but it's pretty close. And I call it collective learning. And it's this. What makes us different is not that we communicate, not that we have language. Many species have language. Many species even have culture. Chimps have culture. It's that we've crossed a threshold in communicative efficiency. Beyond that threshold, well, below that threshold, as much information is lost as is accumulated. So the cultural achievements of chimps appear to be fragile. We can be sure about that, because if chimp culture was cumulative, we would have seen the results over time. Now, human culture is cumulative. We've crossed a threshold beyond which our capacity to exchange ideas is so efficient that these ideas accumulate from generation to generation. That means we're talking about the first species in 4 billion years in which information accumulates within the collective memory on a scale of generations. Now, if I'm right, just crossing that very subtle threshold, it's like a phase change, is of profound importance. And it is what makes us different. So let's link this to energy flows. In the Paleolithic, we have exchanges of information, small communities exchanging information. And we know the results of this. Information accumulates at the species level. And we know that that leads to humans spreading into different niches in a way that chimps don't, and I'll show that in a minute. Most of the ideas generated by collective learning may have been pretty trivial. They may have included jokes, they may have included, styles, hairstyles and things like that, or minor changes in ritual. But some of them were like gold strikes. They were spectacularly influential. And two great clusters of energy technologies were crucial here, and they led to thresholds in human history. The first is agriculture, creating the organic energy regime 10,000 years ago. And what agriculture did can be described quite simply. Farmers rearrange their environment, and they do it with a very particular purpose, so as to increase the production of organisms that they can use and decrease the production of organisms they can't use. Now, the end result is an increase in the energy from photosynthesis, ultimately from fusion in the sun, that is available to our species. So this is like a gold strike. It's the energy equivalent of a gold strike. With agriculture, the flows of energy to human societies increase. And we see the results from 10,000 years ago. Populations rise, surpluses appear for the first time, and they allow us to support wealthy elites. Then a second transformation like this. 200 years ago, the fossil fuels energy regime. We stumbled into a new energy bonanza. What we stumbled into was technologies that allowed us to tap energy that had accumulated not over just 30 or 40 years, but over 300 million years. The difference is 7 orders of magnitude, roughly. Now, this is the fossil fuels revolution, and this, I'll argue, is what made today's world. So, back to the Paleolithic. This is what happens in the Paleolithic. This is the world of chimps. No long-term change. That is normal animal behavior. We'd see it if there seriously was long-term change. This is where humans evolve. And then in the last 100,000 years, they slowly spread. Now, each of these migrations implies innovation. They're spreading into new environments that require new technologies. They exploit new plants, new environments. They move eventually across the oceans to Australia from 60,000 years ago. And that, by the way, is increasingly looking like the best date for the earliest settlement of Australia. They settle in the north of Ice Age Siberia. Now, that really requires very skillful technologies. So collectively, human technology is growing in this period. We often don't think of the Paleolithic in that way. And we can measure it by migrations around the world. That's what these migrations mean. Neanderthals and Homo erectus, by the way, may have been just on the cusp of this threshold of collective learning. Here's the range of Homo erectus, about 600,000 years ago. Here's the range of Neanderthals. It looks as if they were almost doing collective learning, but here's the range of modern humans. We seem to have been just further along that threshold. And eventually, of course, they became our first victims, as it was almost certainly competition from us that wiped them out. Here's agriculture, and here's the big history perspective on agriculture. Fusion in the sun. Energy pours from the sun into the biosphere. It's captured by plants, and one species, us, diverts more and more of that energy to our own use. And the result is, with more population, more energy, more food, populations grow, societies grow denser, they get more complex, we have cities, states, and empires, all the things that get the pulse rate of historians speeding up, accelerating. But energy from photosynthesis was limited. And here I'm relying on what I think is the immensely important work of E.A. Wrigley, the English historian. This is what he calls the organic energy regime. For 10,000 years, roughly speaking, human societies extracted energy more and more efficiently from wind, water, wood, and human and animal labor. This is energy accumulated over 30 years or so. If you burn a piece of wood, this may be energy that came from the sun about 30 years or so and was trapped by photosynthesis. That sets a limit to growth. And here are the results of this limit. Over 10,000 years, I think the evidence is becoming increasingly strong. There was growth in populations. There was not growth in per capita income. And that's why for almost 10,000 years, you have wealthy elites, but the vast majority of society is still living pretty close to subsistence. This graph just captures the period from about over almost the last 2,000 years, and it's from the statistics of Angus Maddison, who's done a lot of work on long-term statistics. These are the limits to growth under the organic energy regime. Then here we have the modern era. That spike is driven by something very, very spectacular indeed, and I think it's fossil fuels. So what happened? If I'm right, there was a second energy bonanza. Let's think of it like a gold strike. We stumbled on 300 million years worth of energy. We discovered the technologies needed to tap it. E.A. Wrigley makes the point that an industrial revolution is physically impossible without access to energy on a scale that does not exist and cannot be secured in organic economies. And he makes the further point, we mentioned Adam Smith this morning, that the classical economists, Adam Smith and Ricardo, did not expect long-term growth. What they expected was that markets would deliver increasing efficiencies within the limits of the organic energy regime. They expected growth to eventually slow down. And that's Wrigley's argument, until we get fossil fuels. And here's a graph from Wrigley showing the history of England over the last 500 years. That red line marks, roughly speaking, the limits of an economy driven by the organic energy regime. And over on the right there, you have Italy in the mid-19th century, still operating under those limits. But what you have in England is something very strange indeed. England escapes those limits. Holland in the late 18th century apparently doesn't. Rates of growth are slowing. Coal is being used in England increasingly from the 16th century, first to fuel industries that require heat, such as brickmaking, glass-making, brewing. So they're already transformative in a small way, and then you get mechanical energy, that you get the steam engine. And now what fossil fuels are doing is not just providing the equivalent of increasing woodland for fire, they're providing free labour, a virtual labour force. And here's the growth in fossil fuels globally in the last 150 years. Now, that graph itself, I think, is astonishing, and I think in the humanities we've not fully taken on board its implications. Here are energy flows through modern human society. This is collective learning in the Paleolithic era. For most of that era, humans were probably accumulating enough per capita to keep going with a tiny surplus. This is normal behavior for organisms. With agriculture, we know they were accumulating a bit more because we have surpluses. With fossil fuels, some estimates today suggest we are using per capita about 100 times the energy we need to survive. No species in 4 billion years has done that. So each of us has 100 energy slaves at our service. They flew me down from Sydney yesterday. I hope some of them will be flying me back tomorrow. They service us. They support us in this modern era. Buckminster Fuller, by the way, used this image of energy slaves. And we're the first species in 4 billion years to behave like this because we've tapped into this supply of energy. Now, if I'm right, this ought to transform how we think about modernity, suggests an old debate, a new perspective on old debates. As a historian, I've learned all my life that modernity was driven by increasing market efficiencies which drove innovation. That's the story Marx told. It's the standard story that of most historians. But that's a story that works for a history discipline that excludes the biosphere. If I'm right, modernity arises instead from a sudden transformation in our relationship to the biosphere. And that means to understand modernity, we have to see history in the context of the biosphere. So this is what an alien paleontologist might see if they were flying over the planet for several centuries. Suddenly, they'd see the planet lit up, and they'd think something very sudden has happened. And this creates the Anthropocene Epoch. So this brings me to the Anthropocene. Now, if I've got this right, what I'm saying is, really, it's fossil fuels, stupid. It's not market efficiencies. Market efficiencies may have given us the technologies needed to tap those fuels, but without those fuels, we do not have modernity. We don't have any of this stuff around us. That's what creates the Anthropocene. I love this image. It, for me, captures some of the strangeness of this epoch we live in. So in the last 200 years, we've become a planet-changing species. Now, I'm not going to spend a long time on describing this. I am going to assume you all know. So I'll just list some of the impacts. We often forget about nuclear weapons. They're still there. There are hundreds of them that are on hair trigger alert. If released, they could seriously degrade the entire biosphere within 24 hours. They're there, and they're ready to be used. That's a measure of our planet-changing power. We're transforming global climates. We're transforming landforms. I did have some statistics, but at least 50% of the surface, of the land surface of the Earth, has been messed with by humans, and I think the actual figure's higher. We're turning the oceans into acid, and there are sharp reductions in biodiversity. Now, again, I don't think I need to go through this sort of gruesome list of of negative things we're doing, and there are things that are potentially dangerous for our future. We may control 40% of the biosphere's energy income from photosynthesis, plus we have the bonus of fossil fuels. Okay, so how significant are these changes? I've given one measure. If I'm right, these changes are significant on planetary scales. In 4.5 billion years, our biosphere has not seen anything like that. Now that already, I think, is a measure of, that's putting human history in a powerful context, I think, and giving us something to really think about. Will our impact show up in, say, 100 million years? There's a wonderful book by Jan Zalasiewicz. He's an English-based paleontologist who argues that yes, they will. An alien paleontologist, it's called The Earth After Us, an alien paleontologist using the tools of modern paleontology in 100 million years will be able to figure out, without great difficulty, that something about what happened during this period. They will notice several crucial things. First, a sudden homogenization of species throughout the world. What you'll see is different species in different environments, and then, like that, it'll be instantaneous in the paleological record. You find the same species all around the world. That will be one thing they'll notice. Secondly, a rate of extinction comparable with the other 5 or 6 major extinction events. And if their chronological techniques are precise enough, they'll figure out that this happened in just a century or two. That's almost the speed of the asteroid that wiped out the dinosaurs. They'll notice ocean acidification, because what that will do, that will show up in a missing layer of limestone. We can actually see similar missing layers of limestone looking into the past. He argues that coral reefs, the decline of coral reefs, will be one of the easiest things for them to see in 100 million years' time. I thought I'd spare you depressing statistics on declining biodiversity. My son sent me this Larson cartoon. It's worth taking a moment to read it. But I think it captures the story pretty well. So you thought dinosaurs were mythical creatures. One of our first victims, apparently. So if I've got this right, this is an astonishing moment in the planet's history. It's not just interesting in terms of human history, it's in planetary history. For the first time in 4 billion years, a single species dominates change on our planet. That's what the idea of the Anthropocene is telling us. And that means that the future of all other species will be affected by decisions made by the next few generations of humans. Now, so here's my question for the humanities. Now, if I've got this right, and of course it's possible, I suppose, I've got it completely wrong, but if I've got this even roughly right, I think the humanities should be interested, because this has a great bearing on the question that CHASS is asking in its logo. This ought to be very interesting for our understanding of humans. Why has it largely been ignored within the humanities? Not completely, by the way. The Academy of Humanities has recently run a seminar on the humanities in the Anthropocene, but I think the scale of the significance of this change has largely been ignored. We've not really taken it on board. Why? Well, here's a quick and dirty answer to that. Historians operate at, and I'm going to talk about historians here, but it's not just historians, at what I call the quantum scale. So let me explain what I mean by that. In physics, physicists understand very well the difference between the quantum and the classical scale. So at the quantum scale, everything is contingent. You really cannot predict when an individual atom of uranium-238 will break down. That's utterly contingent. So if you narrow down to the subatomic level, you're in a world of contingency. But if you move back and you're dealing with, say, 1 billion atoms of uranium, suddenly everything starts behaving much more deterministically. You're not in a contingent world. You can be very certain that in 4.46 billion years, half of the atoms in a lump of U-238 will have decayed. And that's why we use these processes for dating events in the geological past. Many of those dates I gave at the beginning of this talk were based on these sort of techniques. Now, I believe that historiography too has its quantum and its classical scales. Quantum historiography is dominated by, let's call them biographical timescales, months, years, even a century or two. That's the scale most historians work at. This is Fernand Braudèl's Histoire événementielle, forgive my bad French pronunciation. At this scale, individual agency and contingency rule. It's very hard to see large patterns, and most historians resist attempts to do that. Marx famously tried to do this, but didn't convince the history profession. So most historians, in fact 99.9% of historians, work at the quantum scale. So what they see is contingency and agency. The classical scale in human history is only apparent if you move to scales much larger, actually, than Braudèl's longue durée. I would say you start seeing them clearly once you move to scales of several millennia. And not many historians actually operate at those scales. But at scales of many millennia, you're in a classical realm. Suddenly, law-like, quasi-deterministic patterns start to dominate, such as the pattern of human population growth. And I've shown this graph already. I defy anyone to explain that graph by talking about contingency and agency. There are large deterministic processes going on here. And I would say they have a lot to do with what I've called collective learning. So the humanities too, if they go wide enough, will find they too have to deal with both a classical and a quantum realm. And they need both those realms to really get purchase on this central problem of what makes humans different, because many aspects of humanity can only be seen clearly on the classical realm, as I've tried to argue. In all fields, indeed, I think rich understanding involves both looking for the very large patterns and the often contingent detail. The humanities have concentrated overwhelmingly on the contingent detail. But to see the large patterns, we need to link up with the sciences, and we need to go to larger scales, I think. And as I hope I've shown, it's not that difficult. So the CHASS spiral takes us both inwards and outwards, and I think the humanities need to do that. And of course this links with the problem that C.P. Snow articulated famously in 1957. What he argued is that the humanities and the natural sciences were like two different cultures. They couldn't understand each other. They talked languages that were different enough, or dialects that were different enough. They just couldn't even talk to each other. And he regarded this as a tragedy, a bit like the Cold War, because he said the amount that we have to gain by learning to talk across that divide is colossal. Here's how he put it. The clashing point of two disciplines, subjects, when they meet, two cultures of two galaxies, so far as that goes, ought to produce creative chances. In the history of mental activity, that has been where some of the breakthroughs came. The chances are there now, but they are there, as it were, in a vacuum, because those in the two cultures can't talk to each other. And I think 50 years after he said that, it's still true to a remarkable extent. So I'm ending. This is a plea for scholars in the humanities to actually engage with the natural sciences in the large scale. They won't lose their soul. The question about what humanity is, what makes humans different, that question will be there. And scholars in the humanities will be in the best position to offer answers, but they do need to engage with the sciences. And the natural sciences, I think, have a huge amount to gain from the humanities, because in the humanities we're used to grappling with this staggering level of complexity that doesn't yield the sort of mathematical solutions that natural scientists look for. So I think there's a huge amount to be gained by bringing together these domains and these different scales. And I thank you for your attention.
Please do stay and take 10 minutes of questions.
Okay. So I'm very happy to take questions.
Trevor Hogan from Macquarie University. Can I be greedy and ask two questions? The first one, is there a post-fossil fuels energy future for us? And secondly, you mentioned Braudèl and the environmental history in our school as being limited in the structural analysis of environmental history. What about the world historians and the long tradition of civilizational analysis?
Yeah.
It's still a very strong tradition.
Fossil fuels, I actually, trying to keep this lecture short, I cut out a slide that I had, which is from my friend Joe Voros, which is fossil fuels in a big history perspective. So it shows fossil fuels on a scale of, 10,000 years? I can't remember. And how is it more than that, Joe? Anyway, you've probably seen similar graphs, but it shows fossil fuels use. I showed the upturn. What, of course, that shows is a spike that then goes down again. Now, many scientists, I think, would be optimistic that we'll fill in the gap in that time. I'm less certain, precisely because it has this quality of a bonanza. It's like a gold strike. In fact, I think more and more the metaphor of gold strike is a very precise one. You strike gold. One person strikes it. It's serendipitous. They just are looking in the right direction. Then everyone else comes there. Then everything has changed. And then you start, the chaos of the gold fields is more or less the world we're living in again. And then eventually everyone knows the field will be worked out. So I think this is perhaps a much better metaphor for thinking about modernity than this model of market efficiencies that have given us, that the economists have supported very powerfully. And that's a model that suggests, markets are getting more and more efficient and we can go on forever. Your second question about Braudel, I'm a great fan of Braudel. He was really inspirational for me, and the idea of the longue durée was powerful for me, and also their geographical perspective and their sense of different scales. I worked on material life in the Russian peasantry, and that was influenced by Braudel. But now, of course, looking back, I think he was pushing in the right direction, but I'm increasingly convinced his longue durée was, the first article I ever published on big history was called The Longest Durée. It was not really big enough. Even with the longue durée, you're not yet seeing the classical scales. Even at several centuries, contingent events can really dominate. I know the American world historians very well. I'm very much part of their community, and I think world history was pushing in this direction. William McNeill, who wrote The Rise of the West, was a great pioneer. He wrote the preface to my book, Maps of Time, and he's a great enthusiast for big history. And I think he sees big history as the next logical step beyond world history. And I have to say, I admire the American world historians very much. But I also have the uneasy feeling that many of them thought it was such hard work persuading their colleagues that it was worth looking at the whole world, that at that point they ran out of puff. And they thought, oh my God, going to biology as well, and then geology, no, that's really one too many. David, good luck to you, but I'm not going to go there. I think it's a shame, because going for broke, which is what big history does, having a go at constructing a story of everything, even if you get it wrong, has the potential to bring a lot of questions into a sharper focus. And I fear that world history is sort of losing its way. More and more of the scholarship is actually very bitsy. It's getting ground down by the sort of siloized traditions of the academy. And I think that's very sad. I think I've seen gender history go the same way. I've seen environmental history go the same way. All sorts of breakout disciplines. And I'm terrified that big history could end up being siloized in the same way and lose the sense of a large story. So I once gave a paper called Escape Velocity, and my argument basically was, if you want to go for large scale, don't try to creep up on it. That's a bit like throwing something up and realizing you need a bit more power, then adding a bit more power, it's still going to come down, then adding a bit more. No, the way to do it is to go for broke and achieve escape velocity. And I think that's what big history can do. It goes for such a large scale that eventually you find yourself coming back down the scale to human history. And when you do that, I think you see it in new ways. And I hope I've illustrated that in my talk. Yeah.
Thank you. I'm Fiona. I'm a philosopher, so I may not be able to articulate the substance of my question. I think most of it's been answered. But you seem to also be indicating, a limit to the level of complexity. And
yes,
that's what I'm interested in.
I think cosmologists and physicists would both suggest there is a limit, because at the moment, and look, I'm a historian and a science nerd. I read good popular science, so I'm not saying this as a certified cosmologist. But the conventional wisdom is that if you look to the remote future of the universe, what's going to happen is as the universe is expanding faster and faster and faster, so these energy flows are going to get, and this is non-scientist language, they're going to get thinned out. There's going to come a point where in any particular region, those energy flows are so thin, you cannot sustain existing levels of complexity. So eventually, and we're talking trillions of years in the future, complex things will start breaking down again. And the ultimate future of the universe is increasing simplicity. But that still leaves a future of many billions, perhaps hundreds of billions of years, in which we just have no idea what forms of complexity may appear. But it's a pretty good bet if I'm right that complexity builds on complexity, and if I'm also right that the appearance of a species capable of collective learning represents a new threshold in complexity, that is going to be the building block for the next step. I, in fact, have given a paper 2 or 3 times which flirts with astrobiology, and the question is about the Fermi question. Why have we not seen alien civilizations? One possibility is that collective learning yields species that eventually are going to do themselves in. You know, and some of the statistics on the Anthropocene make that all too plausible. But if there are clever species out there, species capable of collective learning, they'd have had to get through this bottleneck, which is the bottleneck of the Anthropocene, to be able to communicate. I was in Oxford 2 weeks ago talking at the Human Futures Institute. They spend all their time thinking about this. And their argument is we should be very scared if we contact aliens. They'll be much cleverer than us, and they'll treat us the way we treat domestic animals. Ditto for artificial intelligence. We should think very hard about creating very clever machines. Now, I'm sorry, I've drifted a bit from your question. Yeah. There's a... Oh, okay.
Helen Farrell is my name. I'm just interested in your concluding slide here, where you're calling for a merge, partnerships in humanities and natural sciences. And I think Professor Chubb this morning concurred with that view by saying that in our research efforts we need to engage right across all our 4 learned academies. How do you see the challenge of that? Because to me that's a huge challenge to develop that. And one of the research that I've read about those challenges includes developing common language.
Yes. Yes.
Would you care to comment further on that and the challenges and the complexities of that, please?
Yes, I think the challenges are huge, but I'd like to think that our big history project, by the way, I think I mentioned earlier, it's now being taught. This syllabus we've devised is being taught in 100 schools in Australia, 300 in the US. Our hope is that it'll be being taught in thousands of schools. Now, those kids have no resistance to this idea of a unifying story. It just seems completely natural to them. So I'm tempted to say that if enough schools teach this, that generation will not have a problem. And the second thing I'd be tempted to say is that yes, in the course of developing this story, and I've been teaching this for 25 years, and slowly, it's not just the story that's come into focus, and I'm not adding anything new. I mean, I take the cosmologist story, I add it to the geologist story, and so on. But what I've been forced to do is something that the specialists often are not forced to do, which is translate the lingo of one discipline into the lingo of another. And what's slowly happening within big history, and there is now a community of scholars working on this, is we're beginning to realize we are developing a language that works across disciplines. I've already used some of its terminology. Energy works very well across disciplines. Increasing complexity. It's not a jargon phrase, but it's one that works well across many disciplines. There are fascinating ideas that I'd love to explore. Information is one. How does information work all the way from mathematics to physics to to human society. The idea of emergence works very well. The idea of Goldilocks conditions works very well. So I think in a gentle way we are actually forging a sort of vocabulary that allows you to talk across specializations. And of course it has to do two things, that vocabulary. First, it has to be acceptable to the specialists in the field. And I think by and large the language we're using is acceptable. They may prefer, the disciplinary jargon, but as far as I can see, we're using language that's acceptable to specialists. Secondly, it has to be accessible. It has to be something that's understandable to people outside the discipline. So I think we're doing that. But you're absolutely right. The barriers to this sort of research still remain huge. But I'm convinced that they are conventional. They are not intrinsic to the problem. They tell us something about how scientific scholarship in the broad sense has evolved over the last 100 years, not about how it has to be. Yeah.
Thank you, David. Please join me in thanking David. I think he'll agree.
Thank you very much.
Thank you. I'll come back. I think he'll agree that Professor Christian has indeed crossed a threshold of communication with that material.